So okay, so we're talking about this one. So I mean, it's not that much different. The approach is pretty much the same. But I mean, just to give the context, I mean, you've seen something like this. You know, it's a tower in the middle, and it's being held down with 3 wires, and so presumably these 3 wires are pulling. So you're pulling this cable, you're pulling this cable, you're pulling this cable, trying to push this down so that it stays in place. So let's first, that's just for fancy graphics, so let me just replace it with a simple line. It's basically the same thing. So this is basically what we have, right? So we have 3 cables, 1 bar in the middle. So my guess is, which even if we guessed it wrong, I think we can still get the right answer, but my guess is that there would be a similar, let me lock these guys, but it's not hard to assume that there must be a tension in each of these 3 cables, because I think the problem explains it too, right? You're pulling it by the wire. So analyzing about that particular point A, there's got to be tensions in these cables, and then this tower in the middle must be in compression. So that's kind of our guess of what the forces would be. The only force that we know actually that is correct is this guy, right? And maybe I'll put a different color to these. Yeah.
Wait, so I know one of them is in tension, but why are the others suspected to be in tension as well?
Well, first, easiest way to guess is that so if you read the problem, transmission tower is held by 3 wires, right? Wires, cables, right? Same thing. But the good thing about cables is that when you see them in a structure system, you pretty much automatically know that it must be in tension, because you can't really push on a wire or cable, right? So that's kind of the first assumption, right? But let's say even if I guessed it wrong, it's still going to be, at the end of the day, we're gonna still find the correct answer. But anyway, I'm just guessing that these would be tension, and that would be the middle one that's being pressed down into the ground is in compression. Let's put the different colors. But the only one we know for sure is this one arrow that is 630 pounds. And if you get the length of that, it's 63 inches. So it's using the force scale that's shown here. It's hard to see. Let's see. Set view. No. Report the layers. So yeah, that's the force scale that we're using, and this is 63 inches. So now the lengths of each of these arrows, I just kind of drew it, so they are definitely wrong. But what needs to happen here is all of these 4 forces need to be in equilibrium. So I'm going to pull this to the side. So same thing, what needs to happen is the addition of all of these 4 needs to total to 0, and it needs to form a closed fourth polygon, which it isn't now because I just guessed the scale of all of these things and they're most definitely wrong. So that's the only force that we know for sure that's correct. So let's use this as a guideline. So after you've done that, so basically all we need to have is somehow scale all of these guys correctly. Right? So that's closer, but if all of these are scaled correctly, then it must close on its own. So, but we can't really do that out of the whim. So same thing as we did last time is with all the other problems. So it's basically, it's just one, which force we know is different, but the process is exactly the same. So that one we know for sure. So that one we know, so we can lock them down, but these three forces need to start. If you connect all of these three, it should start from here and end right here. So basically that's what we want these three vectors to do, right? So therefore I'm gonna take first, and then let's just assume that, and the order really doesn't matter, but let's assume that this would be the first, and this would be the second, this would be the third one, meaning that first one starts from that start point and third one ends at the end point, and second one just goes from the end point of the first and start point of the third. So I'm gonna kind of put this away for the moment, and let's just think about the first one and the third one, right? So third one must end here. Let's just kind of pull it all the way to the side so that we don't even see it. So first one should start there, whatever length, or it could even be going to the other direction. We don't know yet, but so it's along this direction. So what I'm going to do is basically draw the same exact line, but I would scale it. Maybe show it as a dashed line. So basically, as long as your first arrow, I mean, the only thing we know is the first arrow will end point of the first arrow would be lying on somewhere on this line. So that's kind of all we know. Same thing we know about the third arrow is that if we extend, or actually if we scale this line big enough, so third arrow is somewhere there, right? Basically that second arrow that we pull to the side, what it should be doing is it should be starting from somewhere along. Let's isolate this. So second arrow should be starting from somewhere along this line and intersecting with the third line. Does that make sense? So therefore, what we are going to do again is to, make sure again that we have a line that's parallel to this line 2, that is long enough, which is moving along this first line. So I'm going to color this so that it's the same color. So make sure these are parallel. Basically what we need is a surface that is a sweep between these two. What this surface helps us determine is the intersection point between 2 and 3. So if you intersect this surface and that third extension of that third line, you get the intersection point, and that's where the arrow 2 should be ending. Right, and yeah, the length is shown wrong now, but this intersects the line 1, so it should get cut at the line 1, and also you should scale the first arrow to hit the start point of the line 2, and also we should make sure that this line 3 is scaled correctly to go here. So now we have these 3 arrows, 1, 2, 3, scaled correctly to form this closed force polygon. Right, so now we can feed it back to, so we know that's most definitely wrong, that's most definitely wrong, that was wrong too, but now we know if we move this back to the original point, so that's how they should be balanced. And so if you, how does the, if you go to the assignment, was it multiple choice or you had to enter the number? It was multiple choice, right? Yeah, so it's easier for you. So yeah, so if you get the length, if it's 46.742, it's basically 1 inch equals 10 pounds, so that should be 467 something, and that should be 814 something, and that should be 1572 or something like that. So we should have had
The last one.
Nah, I guess I can't go to it, but yeah, but you've seen it, so I just needed to know if it was a multiple choice. So yeah, I mean, again, I would really sort of, I guess this is due today, right? Yeah, so I mean, yeah, so that you can ask questions also, I gave it to you kind of late. So that makes sense? Okay, cool. All right. So now it's still pretty similar question, but if you went to, let's go back to this file, which was on here, if you want to download them. So we looked at this first sample question last week. It was all compression. So the question 2, you have the same exact geometry, but in this case I'm showing it as a cable, right? So it's hanging from a ceiling. It's sort of like I mean, we don't have one like that, but you know, if you think of like the lampshade or something like that, or it doesn't quite look like one, but let's imagine like you're hanging a steel plate or something like that, with cable attached to 3 corners, and it's hanging from the ceiling. And this plate, let's read the problem, I guess. If you read the problem, it says 36-pound triangular plate is supported by 3 cables as shown. Draw the free body diagram needed to determine the tension in each wire. So basically this plate weighs 36 pounds. So the only extra step that you need to think about is, it's actually kind of profound. So if you imagine something like, this is one of the, I don't think I'll make you do this time. Last semester I had this as a homework and everyone pretty much got it right, so I don't know if it was necessary or, but anyway, if you imagine any random shape, right? Let's imagine like just take a sheet of MDF, like half-inch MDF. If you went to the wood shop, just cut out whatever random shape out of the bandsaw or something, right? So you end up with a plate that's this big. And if you were to hang it, so forget about this image. If you were to hang it with one string, right? So you get to drill a hole and you get to screw this, I don't know how you call it, like eyelet thing, right? So if you have a plate, you get to drill one hole and you get to screw this thing and you tie it with the string and you hang it, right? Sometimes it does this, right? Like for example, if you drill a hole here, right? If you tie a string, it's gonna do that, right? But there's gotta be some point where you can hang with one string completely flat, right? And actually there is only one point in, no matter what shape you draw, if it's a 2D shape and if it's a flat, there's only one point. It's different depending on what shape, but no matter what shape you draw, there's only one point you can hang this and hang it completely flat. And that point is, in this case, that's the geometric centroid of whatever you cut out. It's actually center of gravity, but so center of gravity and geometric centroid is not synonymous, but in this case it's the same because your material is uniform. So for example, if you have a plate which half of it is made out of aluminum, half of it was made out of wood or something, then your geometric centroid and center of gravity is different. But if we assume the material is uniform and density is uniform, then basically the geometric centroid is your center of gravity. Anyway, so it kind of looks like this is drawn randomly, but the only point I can hang this completely flat is above the geometric centroid. So that's a vertical line that's drawn from the geometric centroid of this triangle. And so even if it's 3 wires, right, if you had a random length, if you, for example, if you made that string half as long, you end up with this sort of if you tie 3 strings and hang it, it's gonna do this, right? So the only way to hang this triangular plate with 3 wires and to hang it completely flat, that point where you tie 3 of your strings has to end up directly above your geometric centroid. So the only way to hang this completely vertically is, of course you can make the strings shorter, but it would be, so if you look at this diagonal one, so it would have to be along, hold on. So you can hang it here, you can hang it here, So anywhere as long as that point is right above the geometric centroid. But for example, if you did this, it's not gonna hang flat. It's gonna do, right? So still, even though I'm not gonna require you to do it, if you wanna do something like this just to test, right? Just cut a random shape and put 3 holes and try to hold it flat. You can't do it with random lengths and random location. It always ends up being right up above your geometric centroid, and the lengths of these 3 cables must be kind of carefully chosen. But anyway, just to show you that, just to explain that, so that this is not just randomly drawn, right? So this is actually directly above the geometric centroid of the triangle, and with Rhino, it's easy to get the centroid. You can just grab a closed form and type in area centroid, and it gives you a point. Same thing if you had a random shape. Nah, that's kind of messed up. Even for something like that, you can get a area centroid. So that's convenient, but we should probably know for something as simple as triangle, you should probably know how to get the centroid manually. So this is how to get a centroid for triangle. Is basically you get a middle point of each, I forgot the term, each line of the triangles, get the midpoint, connect to the corner that's across, So basically, let me draw a random triangle. So you do a triangle, right? Maybe something like that. So basically, you want to have a midpoint, midpoint, and midpoint. And if you connect that to each corner that's across the way, like this, if it's a triangle, you always guarantee that all 3 of these lines intersect at one point. And that intersection right there is your centroid for that triangle. If you type in area centroid, you actually get the point at exactly at the same point. Just doing it again. No matter how randomly shaped the triangle is, if you connect the midpoint, midpoint, and midpoint, if you connect here to there, here to there, always crosses at one point, and that intersection is your geometric centroid of that triangle. So that's good to know. Anyway, so basically, so this is uniformly distributed material and density in the plate. So then, therefore, that's how we know the geometric centroid is center of gravity. So we can assume, even though this entire plate weighs 36-pound force, we can assume that 36-pound force gravity is working from the center of gravity. So we can assume 1 point for this force, and that's how we show the force here, right? And again, right now I'm not necessarily looking at one particular point, but just as a whole, let me hide the first problem because it's kind of annoying. But as a whole, right? So if you have this system, the hanging plate and the ceiling, that cannot possibly be the only force that's working on here, right? If that's the only force, it's going to be a free-falling plate, continuously falling in space. So another force that we know for sure that's there is not showing the line of action, so sorry about that, but if you assume if you remember the line of action that we talked about for the force, so each force has line of action, right? So you can extend that force anyway. So that's a line of action for this force, and this force is pulling this plate down at that point, right? So something's gotta be pulling this whole thing up, otherwise it's gonna be falling down. So luckily we have a support point at the ceiling where all of these three wires are connected to, and that's exactly where this vertical upward reaction occurs. And it is because there's this upward force at that point where it's attached to the ceiling because of this guy, and this guy is not falling, right? Imagine if that whatever that connection, if that connection breaks, it's gonna fall down, right? So overall, there's gotta be that reaction and that gravity force. So now, because we know what forces are acting, I mean, at least as an entire force system, we have equilibrium. So now we can actually look at each node to determine, sure, there's got to be tension in this cable, right? So now we are able to, okay, so that's a little bit, so I might be missing some of the objects, but so again, so now there's this reaction force that we know is there, and then there are, so now I'm assuming if you're again hanging a plate with a cable, right, it's got to be in tension, because if you push the cable, it's not gonna take compression. So we're assuming all of these three cables are in tension, so I'm assuming that the force in this cable is pulling this point away. Same thing. And the process from here is exactly the same, right? So we did, so I guess I can skip that part because we've been doing this many times. So just, anyway, so that's the force we know. And that's the force we know. And we want F1, F2, and F3 to be scaled correctly so that it closes on its own, which it isn't doing right now, but it should be something like that, right? So in order to get that, I'm using this known force, which is 36 upward, and I'm putting two of these lines at the beginning and the end, and I made a surface here, got the intersection, and scaled all three correctly to get, again, I'm missing the cable, but you know what they are, right? So once you scale them correctly and measure the length and apply the force scale, you end up with 13 pound tension here, 14.44. And sure, if you add all these three numbers, it's not going to be 36, but that's because it's a vector addition, not the arithmetic addition. 26, 40, it's about 40 something. So that makes sense. But the only point that I wanted to address was that for tension, you have to assume, you have to know where the center of gravity / geometric centroid, and the only place you can hold it flat is the point that's directly above that. So I do I guess it's not in the homework yet, but the next homework that I will give you, I will have a... Is this one? Yeah. I will have... I might have posted it already. No, I guess I didn't. But in the homework for this week, I'm gonna have a problem where I'll give you the shape of the plate, right? And I give you the weight, right? And I need you to locate this correctly so that it hangs flat. So sometimes people, I think last semester I saw some students do like, so if you drew something like this, right, that's obviously not going to happen in reality, right? So if you try to hang something like this, it's just going to, right? So you kind of have to locate them correctly so that it's, so that's part of your task. Yeah, cool. So 9:46, 30 minutes. I think we'll get it. So far so good. Any questions? Any anxiety? Nothing? Okay, cool. So let's go to so that we cover the centroid. So that's where. Yeah. So these two. Yeah. So that was the file that we were looking at. This second file was the. It's going to be a homework. I haven't prepared the form yet, so you're not going to get it, but you can, if you want to look at the problem, you can look at the problem. And now I want to look at this Iceman problem. So let's open. Yep.
For the question that you showed us, we are allowed to move that up point.
Yeah, it's more like your. Let me see the file.
In X and Y.
Yeah, so it's more like.
Central, on top of the central, right?
Yeah, so it's more like you're actually required to move it so that it's located correctly. So let's see. Let me. Where did it go? Homework. Yes, it's this one. Yeah, so the problem says we want to hang a 36-pound triangular plate from point D using 3 cables, etc., etc. Place the plate and 3 cables correctly relative to point D so that the plate can hang horizontally. Draw the free body diagram needed to determine the tension in each wire. So you are... Oh, so one thing I think I forgot to mention here is you should move this, but I want to keep the height as is, right? So you are required to move this X and Y, right? So that it's located correctly and tensions are correct, but please don't move up and down because that's going to change the length of the cables, and also it's going to change your answer, right? So I mean, if you move it up and down, your answers would be off. So just to move it X and Y, I think. All right. So now, if you open this file called sample Iceman problem, which you have this one. And there's an explanation in this image, which is directly under here. So this poor guy, in trying to move across a slippery icy surface, a 180-pound man uses 2 ropes, AB and AC. Anyway, so there are 2 ropes, and this guy's moving on this slippery icy surface. And knowing that the force exerted on the man by the icy surface is perpendicular to that surface, determine the tension in each rope. So yeah, so you see the picture, right? So the guy is hanging with the rope. I mean, it's kind of classic textbook type of problem, right? It's like, yeah, I mean, I get it, but how did that happen? It's like, I can't, yeah, anyway. I mean, he's gonna lose his grip at some point. But anyway, so you have these two cables, the poor guy is hanging, and so our job is to basically determine what forces are acting, right? So one we know for sure is gravity. I mean, for convenience, I mean, it's gonna be at the center of gravity for this guy, but let's just assume that gravity is working at that point A, right? So let me hide the guy because he's kind of in the way. But anyway, so you have this completely flat surface with no friction whatsoever, and hold on. And then you have this point A where the guy is hanging from. So there's got to be a gravity, but gravity is always vertical down, right? Like even if I'm like lying on a sloped surface, my gravity is always vertical down. And so what forces are there, right? So if I'm hanging onto these two ropes, I'm hanging onto these two ropes, right? So there's got to be some force in these two ropes for sure, and that's most likely tension, right? Because you can't push on these ropes, and there's nothing, right? So, and there is, however, another force there, and that's kind of the point of this problem. But anyone can guess? Normal force, yeah. Who was it? Yeah. So, well, so one, if this icy surface is not pushing back, right, I will be sinking into this snow or whatever. But apparently, I'm not doing that. So this surface has to be pushing me back. And what's the direction of that force, right? And the name normal suggests that. But to explain what normal is, do you want to?
Equal and opposite.
That's a reaction, right? So, but word normal, if you like look at Wikipedia or something, it means basically perpendicular to something. Like you can get a surface normal in Rhino. That's always like if you have a curved surface, it's always like this like perpendicular. So word normal basically means perpendicular. And so apparently there's a force pushing me back up, but that's actually not this direction, but it's gotta be perpendicular to this guy. So let me also, I think I also posted a link to normal force so you can read that. But anyway, so the force that's pushing this guy up is a normal force, and first we want to kind of draw the direction of that. The easiest way to do that is you can actually go to this polyline tool, and you have this icon that looks like a stick is coming out of a ball, that's the line surface normal, and you can click that and select surface or polysurface for normal line, and I can click on this surface. Start of line obviously is A, and I can, so basically automatically now you're snapped to being a normal surface, normal line for this surface. So that's basically a direction of that normal force. But I mean, just to kind of elaborate a little more on this normal force, I thought there was a video, but I couldn't find it. But the best way to kind of experience what this normal force is, because it sounds slightly counterintuitive that this sloped surface is not, because you would tend to think that it's gonna, if I'm being pulled down, it's gotta be pushing me back up, but it's actually pushing me perpendicular to its own surface. So I mean, it's kind of a little bit hard to grasp, not so intuitive notion. But the best way to find out is if you made like, find some sort of like 45-degree angle. I mean, if you made some sort of 45-degree angle out of wood or something, or you find a sloped surface, it's gotta be a significant slope, right? Like 30 degrees or 45 degrees. You have this scale to get your body weight, right? So for example, if I place a scale at a 45-degree angle and make sure that it doesn't slip off, right? So you need some sort of a stopper. But if it's like, fixed and on this sloped surface, and I weigh about 150. If I step on this scale on the sloped surface, it's not going to read my weight. It's going to be significantly less, because what's happening, so let's kind of put this aside for now, but what's going to happen is, let's say if I put, alright, so my weight is so let's say 1 inch. That's annoying. Let's say 1 inch represents 1 pound. So if I weigh 150 pounds and I'm standing here, then so that's a reaction, and actually that's not good. Anyway, so if my weight, let me draw something like person. Anyway, my weight is here. Not a good diagram, but let's forget it. And the reaction would be, the ground would be pushing me back up 150, right? But if I do that on sloped ground, what it's gonna do is, so let's say my my scale is here. What it's gonna read is, so that's the gravity. The normal force is pushing me back at so there's some sort of a normal force this direction. That's not a correct scale, but so that's the applied force, right? So that's down, and so and then the fact that this is not slipping down, there's got to be some force along the direction of, so let's say if you had like some sort of a blocking to stop the scale to slip down, so then this is gotta be pushing back, right? And then that direction is this way. So basically what my scale is gonna read is only that much, which is like 106 pounds. So anyway, so this doesn't explain this whole thing as vividly as if you, so try grabbing a scale and put it on a sloped surface, and if you step on it, it's gonna read less than what your body weight is for that reason. But anyway, so now instead of a block to stop the scale from slipping, this guy is not slipping down the surface because of these two ropes. So now we have force in this direction, force in that direction, and force in this direction, which is a normal force. So we have these three forces counteracting that gravity force. So again, the procedure is exactly the same. So you have this one known force, right? And then you have these three other forces, which I guess I'm gonna have to give a different color to. So yeah, again, same exact process. So I'm gonna kind of go through quickly. So this is there. Again, the order really doesn't matter. So I'm gonna grab first one and second one, and then make the surface between the first one and the last one, and because that wasn't big enough, right, so it should be like a second nature right now, but I'm just gonna connect all of that, do a join, not join, fillet with 0 radius. So that should be all the forces that are acting. So if I bring this back, that's the normal force, and these are tensions in these two ropes. And because 180 was 180 pounds, the normal force again was 148, and the tension in the rope was, let's see, 64 pounds. And this one's only 31. So again, the trick with this one is you have to identify what the direction of the normal force. Otherwise, so before, so the difference between the first one, which we had the compression, all we had to do was figure out the magnitude of these three legs, right? We had the directions already defined. Second one with the hanging cable was that we had to verify that the location of the plate is located precisely according to the center of gravity. And with this one, you have to identify the direction of that 1, 2, 3rd force, which is the normal force that is normal to the surface. So there's a little bit of extra step, but to find the magnitude of all these three vectors, that's kind of exactly the same. So yep.
What was the command for the normal to find the normal force?
Oh yeah, sure. So you can go here, polyline, and grab that one. And I think the command is normal. So you can either click on the icon and grab on the surface, or you can type normal. No?
No, it's under line. Is a command line, then it gives you extra prompts when you type line.
Oh, type line. Ah, okay. Line and
then you do
normal.
Yeah.
Or actually, if you forget those two, another easiest way is if you explode the surface, you can duplicate the border and extrude. And if you extrude a planar surface, it's always going to extrude perpendicular to that plane. So you can again then duplicate the edge from that. That's kind of quick too. And I guess that's all I know. But one way or the other. So 10:05. So I think that's plenty of problems. So I want to use next class, because what did I say? I said February 12th we're gonna do a little test, right? So I'm not gonna introduce a new thing next class. I think it's gonna be sort of, I can have you solve the homework. I will post the homework for sure, and between that and all the homeworks you've got so far, whatever you get in a test is going to be a variation of those, right? So you are not going to have the surprise question which is completely different from whatever we covered so far. So I think I want to use the next session to sort of, for you guys to cover that. Maybe I have you solve the homework questions during the class, and if you have any questions I can answer them, but I'm not necessarily going to cover new material. Yeah.
Where is the syllabus located? Dates or...
Yeah, should I post it on here too?
Yeah.
Okay. So, right, so I'm gonna go, okay, I'm just gonna do syllabus. And I think I'll also post it on Moodle, although I'm never gonna use Moodle. I think I'm kind of obliged to.
No,